Thank you, Trent, and thank you, everyone. I will start by paying tribute to Doug throughout his collection of books that I had the chance to be acquainted with. This one here is one of my all-time favorites, including, of course, the well-known design theory survey with Jeff. The cryptography book, there are many books in cryptography, but this one I've seen it being taught at classes at various universities in Europe, in China, here, there. So what's the difference? Well, the difference is that this book has two characteristics that not many other books have, and these are clarity and substance. This book here, Combinatorial Algorithms with Don Kreher, again, very helpful for my career as well as the career and research of many other people in design theory. And recently, I found out that yet another book, Techniques for Designing and Analyzing Algorithms, so an amazing productivity. Thank you, Doug, for all this work. And well, now that Corona is over, we can take off the mask. At least I can. And by the way, Corona is now taking back its usual meaning, which is it's a Mexican beer. Okay. Apparently, you can get an 18 pack somehow. In any case, I would like to continue on with my talk and talk about Lesandre pairs and quaternary Legendre pairs. But I will start with Lesandre, the usual Lesandre pairs. The story begins with the Lesandre symbol. Of course, in this classical book by Lesandre on number theory, he defines the Lesandre symbol, alpha over p, for integer alpha and an odd prime p, basically to be plus or minus 1 or 0, according to whether or not alpha is or is not a quadratic residue mod p. So this is the usual definition here. Quadratic residue means there is an x, so that x square is congruent to alpha mod p. The definition from Lesandre uses this explicit formula here. This is just a quick reminder from number theory and some examples in Maple. Coming from Waterloo, of course, one has to use Maple, and I have been using Maple since 1995. So you load the number theory package with number theory. Lesandre symbol 2211 is 0, because, of course, 11 divides 22. Lesandre symbol 911 is 1. 9 is a quadratic residue, mod 11, and 10 is a quadratic non-residue, mod 11, so you get minus 1 over here. These are some simple examples. And this is an extract from the original book of Lesandre, and if you can read this small print here, comme les quantités analogues, etc., se rencontreront fréquemment dans les cours de nos recherches. Okay? Amazing clarity in his definition a few hundred years ago. And let me, no, he didn't call it, no. It was called later by others. He didn't have a name. But he says clearly, we will use the abridged character N over C. It's a very, very clear definition, which is, of course, the same since then. So there are two ingredients that we need to define Lesandre pairs. It's an extremely easy definition. The first one is the periodic autocorrelation function, which sometimes we abbreviate as PAF. In the literature, in IEEE journals, they have other abbreviations, but it's the same function, of course. So if we have a sequence alpha of length n, then the periodic autocorrelation function is defined up here. PA of S is defined for every S from 0 to n as the inner product of the original sequence and the sequence translated in a cyclical manner by S. there is a well-known symmetry property of this path function, which is important for computational purposes. This one here essentially tells us we only need to know half of the periodic autocorrelation function values. The other half are equal to the first half. And there is also another property that relates the sum of all the periodic autocorrelation values is twice the second elementary symmetric function on the elements of the sequence. All of that is useful for computational purposes. And the second ingredient that we need is the PSD, the power spectral density. How is this defined? Well, this is the definition of the usual DFT, the discrete Fourier transform. So if we call the elements of the discrete Fourier transform associated with a sequence, if we call them mu0, mu n minus 1, where this is the usual definition with the omega, the primitive nth root of unity, okay? Then the PSD of the sequence at, let's say, argument k is simply the squared magnitude of this complex number. In other words, the sum of the square of the real part and the imaginary part squared. So a very, very simple definition. And we thought we are ready to give the definition of Lesandre pairs, which appears in this HAC paper, the Australasian Journal of Combinatorics in 2001. For every odd n, if we consider two sequences A and B with n elements, all of the elements are plus and minus 1. We do this normalization. The sum is equal to 1, and the sum here of the BIs is also equal to 1. So both sequences have element sum equal to 1. And also if the path, the respective path values for every S sum to minus 2, from 1 up to n minus 1 over 2, remember n is odd, okay? Then we call this pair of sequences a Lesandre pair, okay? So very, very simple definition. And the first remark that we need to know is that this path constancy property, or path invariance property, if you like, implies a relationship between the PSD values of the two sequences. So we have that the sum of the PSDs for every S from 1 to n minus 1 over 2 is equal to a constant, only now the constant depends on n, and the constant is 2n plus 2. So to summarize, Lesandre pairs are characterized by two invariants, the path invariant with the path constant minus 2, and the PSD invariant with the constant 2n plus 2 for every odd n. So again, very simple definition, right? And these are some examples. For n equals 11, the PSD constant is 2 times 11 plus 2, 24. This is A and B up there. The first path values, 5 path values for A are all minus 1s. That's a fortuitous coincidence. And the first path values for B, lo and behold, they're also minus 1. So of course you recognize some sort of difference set there, obviously. And the sum vertically is always minus 2. Now another example, n equals 13, another prime. Now the first 6 path values are 1, 1, minus 3, and so on. And the other path values underneath minus 3, 1, 1, 1. The sum vertically is always minus 2. Okay? And here's another example, a bigger prime, 37. Again, the first 18 path values of A and B match. The sum is always minus 2. But now I want to show you the PSD invariance, also how this materializes. These are the PSD values in this column for A, and in this column, the PSD values for B. And when you sum them up, you always get 76. And this is an exact summation in integer arithmetic. You get exactly 76. And of course, it doesn't take long to realize that if you look at these numbers, there are only 2 different values that appear. And this is explained by an easy Gauss-Sum argument. If you remember the definition of a Gauss-Sum, it's a sum of Lesandre symbols with some coefficients, right? So this is the connection between the Lesandre pairs and the Lesandre symbol, it turns out that for every odd prime number, so if the length n is a prime, an odd prime, we're not concerned with 2, then this construction here, so we take the sequence of the Lesandre symbols I over p, for I from 1 to p minus 1, we prepend 1 and 1, and we take the negative of this sequence that we constructed. Then A and B is a Lesandre pair for every prime p. So we can dispense with all the primes right away, because there is an easy construction that you can write down in a few lines, 4 lines of Maple code, right, that works for every p, for every prime p. And once we have, and moreover, once we have a prime p and a Lesandre pair of order p, then we also get a Hadamard matrix of order 2p plus 2. Okay? How is this done? Well, this is done by taking the Lesandre pair and making circulants. So this is CA up here and CB, and then the transposes. We make 2 circulant matrices A and B, where the first rows are exactly the Lesandre pair sequences. And then this array, supplemented with these rows and columns and the block on the top left, is a Hadamard matrix of order 2n plus 2. Okay, so this is a very simple construction that guarantees that whenever you have a Lesandre pair of order p, or order anything, you get a Hadamard matrix of order 2n plus 2. And in fact, if you think about it, 2n plus 2, when n goes through all of the odd numbers, is exactly the range of multiples of 4. Therefore, what we can sort of conclude here is that Lesandre pairs furnish a structured version of the Hadamard conjecture. In other words, the Hadamard conjecture is very general. It says there is a Hadamard matrix of order 4n for every n, but doesn't say anything about what that Hadamard matrix could be. And as we know very well, there are hundreds literally, of constructions for Hadamard matrices, and only top experts know all of them. I certainly don't. Okay? This structured version says there is a Hadamard matrix coming from a Lesandre pair for every order which is a multiple of 4. The most significant state-of-the-art computational result in this Hadamard conjecture in general is, of course, Hadi Karagani's JCD 2005 paper, where they resolved the Hadamard matrix of order 428, a very highly cited paper. And there are 2 conferences where I will say a lot more on Lesandre pairs. I invite everyone to tune in to the Zoom. It's free if you like. So the first one is in Krakow, the Hadamard 2022 conference in Poland. This is an on-site hybrid conference in July. And also this enumerative combinatorics and applications conference at the University of Haifa in Israel, which is only online and also free. There is coming back to the primes for a minute, there is a particular dichotomy that I would like to mention, and it's the mod 4 dichotomy. So not all primes are the same, according to these examples that I've shown you. If p is 3 modulo 4, then it turns out that all the puff values are equal to -1. The PSD values are all equal to +1. So when we add them up, we'll get the puff constant -2 and the PSD constant 2p plus 2. So this is the easiest case. When p is 1 mod 4, let's say the 37, then all the puff values belong to 1 and -3. And there are only 2 different PSD values because of the Gauss-Sum argument. And again, we get the puff constant -2 and the PSD constant 2p plus 2. In terms of the computational state of the art, in the search for Lesandre pairs, what we know so far, all odd orders up to 100 have been resolved today. And the smallest open order, for which we don't know whether or not a Lesandre pair exists, is 115. So again, for n equals 115, we don't know whether or not a Lesandre pair exists. Of course, we believe that there is, they do exist, but nobody has been able to find them. For the non-prime case, what can we do? We can use this concept of compression that we created with Dragomir Djokovic, a concept of compression for Lesandre pairs in this DCC paper in 2015. Essentially, we said that if the order of the sequences that we're looking to make a Lesandre pair is a composite number, if it's prime, we're done. If it's composite, then we take a divisor of the order and we create these subsums, which are d apart. So d is a divisor of the order v of the sequence, and we stick them together in a smaller sequence of length d. Of course, the alphabet now is bigger, but that doesn't matter, and we call this new sequence AD the M compression of A. And it turns out that in terms of the invariants, the PAF and the PSD invariants, when you do this compression, the PAF constant of the compressed sequences scales linearly, so it's minus 2 times M, while the PSD invariant remains exactly the same as the original sequences. And again, for computational purposes, this is very, very, very important. I will skip a few slides in the interest of time. I just want to give an idea of how we use compression to find Lesandre pairs. So let's say that we have a Lesandre pair of order 133, which is a product of two primes. Then we can compute the 19 compression, and we find these two sequences with 7 elements each one. They have these properties. Therefore, conversely, if someone gives you those two sequences A7 and B7, and why is that a good strategy? Because those are very easy to compute, and there's very few of them. Okay, so it's a lot easier to work in a space of sequences of length 7 than a space of sequences of length 133. So that's the advantage computationally. So if someone gives you these two sequences A7 and B7 with these characteristics, then can you recover the Lesandre pair of length 133? Computationally speaking, this is possible. Of course, it's time consuming, and programming this algorithm is not the easiest program that I had to write, but it is doable. The only problem with it is that compression is not an one-to-one mapping. What does that mean? It means that if we have sequences with this profile, meaning with these PAF and PSD constants, then they do not necessarily correspond to a Lesandre pair of order 133. Only a small percentage of these sequences will yield Lesandre pairs. But again, imagine that you have, let's say, 50 or 500 of these pairs to check. This is a lot better than working with a space of, again, length 133 sequences. Okay, in the interest of time, I will skip a few things. Maybe mention briefly that in this paper here with Jonathan Turner, Dursun Bulutoglu, and Andrew Geiger from the AFIT, the Air Force Institute of Technology in Ohio, we managed after 20 years to find a Lesandre pair of length 77. This was an open problem since 2001. It took a lot of effort, especially the PhD thesis of Jonathan Turner, who also came to Waterloo and visited me for 10 days or so, and managed to be in my office at 9 in the morning every day. And if I was late, he said, well, you have to be punctual, and we have to collaborate. I drove all this way for you. But anyway, I'm kidding, of course. He's a very nice person. So we managed to do this, and when finally we found these solutions, we observed something. We observed that these solutions are not random at all. they have a very, very unique structural property, which is that when we take 11 compressions of the solution, then these 11 compressions are sequences that have constant autocorrelation, constant, only one value when you sum them up. Okay, and this is again something very non-random. So we uncovered this property, and later in this JCD paper with Christoph Kutzan, who is a German mathematician working in Austria, we elaborated this constancy property, and we finally reduced the list of open cases in these 12 cases, and since then those two cases have gone, the 85 and the 87, so we are left with 115 and up. Okay, so let me get to quaternary Lesandre pairs. This is joint work with Arne Winterhoff, who is a number theorist at the Austrian Academy of Sciences. This is work in progress. The definition that we sort of thought it was a natural generalization of these Lesandre pairs is to allow the alphabet to be, of course, the fourth roots of unity, plus minus 1 plus minus I. The puffs sum to -2, but now notice that we remove the parity restriction. We don't need the oddity of n. N can be, the length can be even or odd or even, rather. And of course, we have to pay attention to the puff definition to use the complex conjugate, otherwise this definition won't work. And the first thing that we noticed is that these quaternary Lesandre pairs are balanced. So what does that mean? It means that if you take the sum, if alpha is the sum of the elements in A and beta is the sum of the elements in B, then we have this property. Therefore, alpha and beta can only be -1 plus 1 I plus I if the length calligraphic L is odd, or they can be other complex numbers over here if L is even. And we focused on the case of even L because they don't exist for conventional Lesandre pairs. And so if we sort of mimicked the construction from AJC in 2001, so if A and B is a quaternary Lesandre pair of odd length L, and we make this normalization that the sum of the elements is equal to 1, then this is a quaternary or complex Hadamard matrix of order 12 plus 1. And similarly for even length, but now we make this other normalization that alpha is 0 and beta is 1 plus I, okay? Then this array gives us again a complex Hadamard matrix of order 12 plus 1. We can also use quaternary Lesandre pairs to produce real Hadamard matrices, but I'm not going to go into that. I just want to give two toy examples how they look like, these quaternary or complex Lesandre pairs. Well, for n equals 2, A is 1 minus 1, B is 1, and I, there is only one puff, the first one, so puff A1 is -2, the other one is 0, so the sum is -2, and we are good. For n equals 15, this is a trickier one to find. You take some computational effort, but in any case, not too hard. These are the 7 puff values for A. You see there are complex numbers and so on in there, but the sum is always vertically -2. So this is an example of quaternary Lesandre pair for order 15. And what are we interested in? We're interested in how to construct these quaternary Lesandre pairs. And one way to do it is to identify appropriate seed sequences. In other words, sequences that we can uncompress into a quaternary Lesandre pair. Remember, I was telling you that the problem of compression is that it's not one-to-one. Okay? So if we have, let's say, a few thousand candidate compressions, then we're not going to go through one by one. This would be silly. In Jonathan's talk, there was a similar argument. We have to do something clever, okay, to narrow down the range of possible candidates. So this is one possibility. We define these sequences AP, which are 0 if J is 0 mod P, and 2 times the Lesandre symbol if J is different than 0 mod P. And BJP is again 1 plus I, and then all zeros. Okay. Then it's easy to see that you can determine the autocorrelation values of these sequences. And if you look at them, you see here the 2 for P plus 2, then the sum of the PSDs is 2P plus 1. So if you remember the 2 compressions, the seed sequences AP and BP provide promising 2 compressions for quaternary Lesandre pairs. And by exploiting this, this idea, here they are. I just wrote them down for you. This is AP and this is BP. To give some idea of the complexity, for P equals 19, the prime 19, there are 2 to the 37 possible 2 decompressions, but this is a manageable number nowadays. It can be, you can do an exhaustive search if you like, or you can just do a search and find a few solutions. For P equals 23, there are 2 to the 45 decompressions, so you need probably parallel computing and so on. And we also use some other, if you like, tricks, which is this anti-symmetry pattern that was noticed by Arne. For the B2P sequence, we can break it out we can break it up into 4 groups like this: M values, then minus these M values, then again minus over here, and then BM up to B1. So we end up with a very small number, M P minus 1 over 2 to work with. And it turns out that using this kind of pattern and complex code for complex decompression, we are able to compute several of these quaternary Lesandre pairs, and we'll see where this takes us. This is all I had to say tonight, and again, happy birthday, Doug.